Hey, this is OXDF, and today we're looking at Whole Lot of Candy. It's a crypto challenge from the HackTheBoo CTF that was put on by HackTheBox at the end of October. And like many of the challenges, we're given both a set of downloaded files as well as a IP address and port of Docker instance to play with. So let's start off by taking a look at the Docker instance they give us. I'll paste in here and check it out. So it says, please interact with the server using JSON data. Selected mode is ECB, options, and then some options. So like I can push one and try to click flag. It doesn't like that. We can try using like JSON data, and I'm not exactly sure. So like option one, like that. That doesn't work. It says response error message option. We could fuzz this some more and try to figure it out, but frankly, because we probably have the source code, let's jump over to that and take a look at that next. We'll just do VS Code. Well, I can show you real quick where we have in this directory, we have encrypt.py and server.py. So I'll open up those in code. Let's start with the server since that's where we're kind of stuck. So we start with these modes. There is a handler class as well as a reusable TCP server class. We have a send message and a receive message function. But I'm not going to dig into them too much to see how they look like they're probably doing very normal looking things, but let's just assume they do what they say they do. We have main here, we'll probably go there, and then at the beginning we're going to say, if main, we're going to start this TCP server. It's going to listen on LEET and serve forever. So, okay, so let's do it main, and let's see, it says, oh, the handler is handler. And if we look at the handler is going to call main on the request. So each request that comes in is going to be passed to main. Or I guess each connection is really the way I think about it. So in main, we're going to pick a mode randomly out of our modes. So we saw before that, here's the mode is OFB, here the mode is ECB, etc. Then we're going to create an encryptor object. We can go back to the top here and we can notice encryptor is imported from the encrypt function. So when we get to looking at that, we'll take a look at that as well. But we'll note that's made right at the top of main. Then we enter a while true loop. And so we're going to send, please interact with JSON. The selected mode is mode. We're going to receive a message. So we're going to send the menu basically and receive the message as payload. We're going to load that payload as JSON. So it's going to have to be valid JSON. We kind of saw that. We got errors when I just typed 1. And then we are going to look for payload sub option, and then we're going to match it against strings. So let's go back here. We can try this now. I'm actually going to do something hopefully useful here. I'm going to do rlwrap here. And what that's going to do is it's going to allow me to do up arrow and get to previous things. So that'll be useful. So we can do things like option, and we saw that we need a string one. So let's try that and hit enter. And it returns the response encrypted ciphertext. So here's the ciphertext. So that's kind of cool. Maybe we can change mode, change option to 3, and that's where rlwrap was really nice because I could just push up arrow and change the 1. That's kind of cool. Expected modes, and so rather than guessing, let's go back and figure out how to interact with this thing. So if I choose option 1, it's going to call the ENC, which is what we imported. Excuse me. And it's going to encrypt it. You encrypt the flag, which was also imported from a file I don't have called secret. Going to encrypt that using the current mode, and it's going to convert it to hex, and it's going to send that back. That's what we saw. If we choose option 2, it's going to ask us to enter some plaintext. It's going to read in some JSON and get the plaintext option. It's going to encode it to switch it to bytes. It's going to encrypt it using the current mode, and it's going to return it. So we can encrypt whatever we want. Option 3 is going to be to change the mode. So it's going to list the supported modes. It's going to receive a payload. It's going to, again, it's got to be JSON. And then it's going to call random.choice on payloads.modes. So payloads.modes is going to have to be an array or a list. So we'll want to note that. And then option 4 is just to exit. And that's about it. Okay, so let's go check out the encrypt function. The encrypt, whatever this is, file. So we have encryptor here. I think that's all we have. That's in this whole thing is a class. There's the init function. Now, init is what in Python, whenever you create an instance of a class, it calls init. And so in this case, the key is going to get self.key is going to get set at that time. So that is right here when this gets called at the beginning before we enter the while true. So each connection is going to have its own self.key, but that same key will be used throughout the whole connection. So that's important to keep track of. Then we have these different mode types. So there's 5 of these, I'm going to guess, to match what we saw listed in the in server. And at the bottom, we have encrypt. And so it's just basically going to do if mode is this, then encrypt, then call the ECB function. If mode is CBC, call CBC. If mode is etc. And then return CT. If I have a mode that doesn't match any of those, I'm guessing CT is not going to exist, and this is going to throw an exception. So we should take a look at these different modes and get familiar with these different modes of encryption. These are all AES modes of encryption. Pull up a so Wikipedia block cipher. I think that's the one. Block cipher here. This is a really useful page for learning about the different modes of block cipher encryption. Let's see if we can scroll down here. I think this is the page. No, this is not the page. Block cipher mode of operation. There we go. This is the page. So we're going to talk through each of these modes and use the diagrams and the labels here as sort of a guide. So I think before we get here, it's worth saying, given the layout of this challenge, what do I know so far? I know that I can get an encrypted flag. I know that I can give it any text I want and get back encrypted values as well. So given that, I'm probably looking for some kind of known plaintext attack, some sort of attack where if I can use the fact that I have the encrypted and the plaintext, that I can recover some sort of key stream that's going to be used again, and I can use that key stream to decrypt the encrypted data, the unknown data. So let's start with that in mind. We'll go through each of these options. So the first one is ECB, electronic code book. And if we look at these diagrams here, I'm going to make this a little bigger. Here we go. It takes each block of data. So a block is typically, think 16 bytes, right? And it encrypts it by itself with the key. And so it takes the key. Now this box here, block cipher encryption, think of it as kind of just a black box. Data goes in, data comes out. And so each block is going to be encrypted independent of the others. And that's what leads to these famous, the vulnerabilities in this is, like if you encrypt an image like this, what happens is every time you have a piece of white, it's going to come through looking the exact same. And so while this isn't the same penguin, you can still see the shape of the penguin here because of the way the blocks work out. And so it's generally frowned upon to use ECB. So let's go look at how are we implementing ECB. We get a new AES object using the key and in that mode, and then we're just going to call encrypt and we're going to return it. Padding to 16 bytes, that's a normal thing. So there's some potential here, right? Can we reuse that? Can we, let's see. So I guess, we didn't check. Oh, we did talk about this. So let's see. This is going to be modes, and then we want to do, let's make it ECB. ECB. Now I'm making this an array like this. That'll work. Yeah, selected mode is ECB. If I make this, if I do option 3 and then I make this not an array, if I just do ECB like this, you'll notice my mode changes to B. And what happens is, it took me a minute to figure this out. It treats this string, when we get to write, let's see, where's server? When we get to modes, we're going to, payload/modes is the string ECB. So random.choice on a string is going to say, choose one of those characters at random. And that's why the mode became B. That will fail if I try to encrypt. So let's go back here and we'll change 3 and then change it here. And again, I'm able to up arrow because I used rlwrap, the lifesaver in this challenge. I don't quite know why they made us interact with it in JSON, but anyway, we will keep going. So we've made it ECB. We can do, we got to do a mode. Let's do a mode 2 and just take a look at it. Enter plain text. What is it? Is it expecting it's expecting the key to be plain text. Okay. So we'll do plain text like that. And let's enter just like a bunch of B's. Good right there. And so we'll run this and we'll get some results. And if we run it again, it would just run the same thing. We'll notice we get back the exact same thing. And so we're getting the same thing. What's kind of cool, what's worth seeing, I'm going to go a little bit probably like overly in depth on this, but like if I go to Python and I do don't get too caught up on this syntax right here, but I'm just going to try to make a point. B be like this. This is a format string where the variable being printed is just the ordinal number of the character B. So it's like hex 42, I believe, printed as binary. And so that is what a B looks like in ASCII, right? It's 7 bytes, and there it is. If I get a C in ASCII, it's exactly the same except for the low bit has switched, okay? And so this whole demo is just to show B and C are 1 byte different. 1 bit different, excuse me. So if I print this again, and I come up here and change 1 bit, like that C right there, just change 1 in this whole string of things, I changed 1 bit. We'll notice that on the end here, it actually looks still the same. Here's 407, lots of B's. Let's see, where can we figure out real quickly where this goes? Here's D, F, F, C right here. So this, starting here and down here, it's exactly the same. But before that, it is completely different. So within the block that I changed a bit, the entire block is completely different. And the reason that's important is it means I can't just like get some key stream from like encrypting a bunch of B's, get back what the keys are, and then go XOR it with the flag, because changing 1 bit just completely changes the whole thing. And that gets back to this whole like, this box right here is complete unknown. If you can't look at like changing 1 bit here or changing 1 bit here makes this completely different. So this is kind of a dead end, and this is why ECB is not going to be useful for us. So for cipher block chaining, what they decided was to get over that problem with diffusion that they showed above is we're going to create an initialization vector. And now an initialization vector doesn't have to be secret, but it's going to be random and never reused. And we're going to XOR that with the plaintext, and then the first block of plaintext, and we're going to encrypt it. And then we're going to take the results, and it's the ciphertext, but we're also going to XOR that with the next block of plaintext, and that way every block is completely different. So we're taking randomness and this, and now we just it'll create complete noise. If we look at how this is done in encrypt, we are getting a random IV every time it's called. So not just at initialization, but at each call, it's going to be a random IV. Beyond that, typically when you use something like CBC, you actually attach the IV at the beginning of the encrypted data and send it back, because again, it's not meant to be secret, it's just meant to be different. And so they aren't giving it to us. So we don't even know this IV. So there's really nothing we can do with this. It's pretty much out of our hands here. So CBC, we're done. We're not gonna make any progress with that. The next one we have is CFB. We'll skip over PCBC. So let's see, Cipher Feedback. Now this is similar, but it's different, because what it does is it's going to turn this block cipher into a stream cipher. And so a block cipher takes a block of stuff and encrypts it, and out comes stuff. Stream cipher, the idea is to generate a stream of random bytes and then XOR those bytes with the bytes of plaintext to get the ciphertext. And that's actually perfectly, if those bytes are random, as long as you can't, if you can't regenerate that stream, you can't, there's no way to get the plaintext back. So it takes an initialization vector and a key, it generates, magic numbers here, and then it XORs it with the plaintext and it's ciphertext. And then the result is also passed back in magic and then a new key stream here. So if we could capture this key stream, we would be in good shape. For that key stream to be the same, though, we need to know that the key and the IV are staying the same. So let's go back here and look, and we are back here, and another time we've got an IV being created uniquely each time. So unless we can recreate it where the IV is the same as the IV that was used to encrypt the flag, which I don't know how we're going to do, this isn't going to really be useful to us. The next one down here is OFB. Let's go here. And this is output feedback. Is basically the same, except for we just changed what's getting passed through. In this case, last time we did the plaintext XOR and then pass things into the next block, and this time we're grabbing it before. But so we're gonna have the same problem with the IV. Without having the IV, we're not gonna be able to do much with it. So, and just to be clear, it is also creating an IV at random each time. Okay, so now we're down to the last one, counter mode. Let's see, so counter right here is another chance to make it a stream cipher. So it's doing that. This time we're feeding a counter into the key, or into the block cipher with the key, and generating, and then XORing with the plaintext, and then we just increase the counter, and so we get completely different stuff out of this and different stuff out of this. The good news for us is that this counter is predictable. So if we can figure out where we are in the counter, we will be able to recreate this key. Well, then the key stream will be the same. And this takes us to the vulnerability here, and that is that at the beginning of each time here, whereas on the other ones it was generating a random IV, this time it's generating just a new counter. So we can go jump real quick back into Python, and we'll do, let's go grab it from the code actually. Where is it? Let's grab this counter thing and import that. And then scroll down here, and we will grab counter new, the counter that it's doing, paste it in, and you can see it creates this counter object. If we run it again, we get another counter object, but it's exactly the same. The initial value is still 1. So we're getting these 128-bit counters, but they are always the same. And so this means that if I send the same text into this CTR, I'm going to get back the same text each time, and that if I can I'm generating a stream, so if I can recover that key material, I'm not going to get this key here, but if I can recreate the data that comes out here at the bottom of the block, then that's all I need to that's all I need to get the ciphertext back to plaintext. So hopefully that makes some sense. Let's write a program to try to exploit this for us. We are going to open up here, and we will go back to our window here with this. This looks good. We'll come down here, and we'll do a vim solve.py. We will import shebang user bin in the m python 3. We are going to import some stuff. We're going to need JSON, clearly, because we're going to be dealing with JSON data. We're going to import sys because I like to pass things via the command line. And then we'll do from pwn import star because pwn tools is by far the easiest way to interact with a socket. Let's see. To start, we'll do something real simple. We'll just say IP equals sys.argv1, port equals int sys.argv2, so that way I can connect however I want. Then we can say r equals remote IP comma port. And so we can do that. Actually, let's just do r.interactive. We can come up here, let's create a new little terminal here, and we can do Python solve.py, and then let's grab off the web page over here on another monitor. You don't get to see it. And opens the connection, and it works. So I'm just going to cut that there because I don't want to interact. I don't want to write JSON anymore. All right, so the first thing we're going to want to do is set the mode to counter. So we'll do r.send after, and we're going to look for this like this, and afterwards we're going to send what are we going to send? So we're going to send the option 3. That. And that should work. We can do r.send after, and then what's it going to look like? I should figure this out. Let's see. So if we do option 3, the next thing we're expecting is expecting modes. We can do b modes, and then there's a new line there. I don't know if there's a space or not, so we'll just try it and see. And then the b is going to be, the b here is going to be, the string here is going to be modes, and then we'll do ctr, that, close, there we go. So there, we're going to, let's see, let's run this and see what happens. We run this, our expectation would be that the Docker didn't die. Let's see. I'll go back and check real quick to make sure that's not. No, it's still up. No, that's weird. It's working. So it's hanging. Okay. So the Docker is not dead. So what this tells me is, let's see. Well, we can try something else here. We can come here and say, we put debug here at the end, it'll run in debug mode. Let's open this up, and it's going to show us everything that's sent over the wire. And so it's sent back expecting modes space new line. And my script, this is a useful learning technique, is sitting here waiting for modes new line. So it's not going to see that because there's no space. And so I'm sitting there waiting, it's sitting there waiting, and we're just stuck. If I put the space here, because that's what it's being run, I can close that and run it again without debug mode. And now we can see we are in counter mode. I guess it's possible we were in counter mode to begin with, but like we can run it a couple times and see that we're always in counter mode because we've changed into counter mode. So that's cool. Okay, so we've made progress here. Next on the script, we're going to want to encrypt some text we already know, like just a long string. So we'll do r.send after. In fact, I'll do 2yy to yank 2 lines and paste. And I'll do dd to delete. And this time we want to do option 2. And now it's going to, let's see, we're going to make some plain text. So we'll say plain, let's just do pt equals b, and I think 64, let's see, a, I think 64 of these will be enough. We want it to be longer than the flag because we want to get enough keystream to decrypt the flag. If it ends up not getting the full flag, we will back and extend this. In fact, we can just, let's just make it 128. Let's go crazy. And so now we don't need modes, but we need after, send after, let's see, where are we? Let's make sure we get it right. Option 2. Now we're looking for plain text. I'm going to assume it goes space new line again, but again, we'll watch for that hang. And this time we'll send plain text. And we want that to look like that. And then we're going to put this break here. I would normally do this like an F string, but we're not going to be able to do an F string. Well, doing an F string with the JSON is going to be ugly, so we'll just do like that. And that needs to be bytes. So we're going to have this JSON that sends plain text, it waits for J to play text, and then it sends the JSON plain text, and then this 128 A's, and then closes it out. We can see what that looks like and make sure it's working okay. And we would expect, now when we go interactive, it's just going to print the rest, whatever's queued up to the screen, so we get back the results here. So we want to parse this. There's probably a slicker way to do this, but I'm just going to do an r.readline to get, let's see, I'm going to show you, to get this line right here. I think it's just one line. We'll try it. And then I'll do, see what we're going to call this, resp equals json.loads r.readline, like that, and we will print resp. In fact, we can print, let's try to print resp cipher text, that, see if we get it. Okay, Control Z, run this again, and we did. So this is us printing that, and then we switched interactive mode, and we're continuing on. So that's cool. We've now managed to read our encrypted text. Get rid of that print. Actually undo. Let's actually use this here. I'll use this down here. Okay, so now what do we need to do? We've got this encrypted plain text where we know the plain text. So now let's go ahead and get the flag. So we will do a r.send. Let's go up here and grab our options from before. 2yy. Paste, dd to delete the line. Now we want option 1. Let's get the flag. And I don't think we need any read after on that one. Let's see. If I do option 1, I just get the flag back. So it's going to look a lot like what we already had. We'll delete this. We will yank that and paste it there. We'll do all this known CT equals, well, oh no, actually, let's do it this way. We'll do cipher stream is equal to, so we're going to do a list comprehension here to create an array. And what our array is going to be, we're going to say zip, and we're going to combine the plain text, pt, with the cipher text. So we need to do, we'll take result dot cipher text, like that. Now, that comes back as a hex thing, so we don't want that as hex string. We want it as bytes. So we'll do bytes.from hex around that. And now we've got we should have the plaintext bytes and the ciphertext bytes. And so what we're going to do is we'll do like P XOR with C for P comma C in. So what this is going to do is it's going to loop. So zip is going to take these and pair them up one to one. So the first byte of plaintext and the first byte of ciphertext, the second and the second, third and third. And so we're going to do this for loop where each time the plaintext byte becomes P and the ciphertext byte becomes C. And then we're going to XOR them. For each byte, we're going to XOR them. So we're going to have an array. Cipher stream is going to be a list of all those XORed bytes. Hopefully that makes some sense. Okay, so we don't need this anymore. So now down here, we're going to read this in and we're going to have response, and that's going to be equal to the encrypted flag JSON stuff. So we can now say flag will do the same thing. Flag equals, and we'll do our thing here. And we're going to start by zipping. What are the two things we're going to combine here? We're going to want to combine response. I don't know why I called it result up there. Better fix that. See? Response of ciphertext. And we're going to need to convert that to bytes from hex as well. Bytes.from hex. That looks good. So we're going to zip that. What we need with the key stream, the cipher stream. So there's our cipher stream and that. Do we have enough? We need another parenthesis there. Do they match up? No. Okay, so that's good right there. So now we're zipping those together. So we'll do for C comma stream comma C in that. Now we're gonna have those two things. We're gonna do S comma C. And this time we don't want integers back, we actually want characters. So we'll turn that result into a character. And we will, assuming it's all gonna work, we'll join all the characters together with an empty string so that we get back the string that is the flag. And now we can do like, let's use success flag, print the flag. And now just to be like clean about it, we can exit, I guess. So we will up here, YY to yank, paste, send option, replace 4. And I don't know if, is there an r.close? Is that how we exit? I actually don't know. We'll find out. So if this works, we will get a flag. We did, although it doesn't like the exit. Just delete this and let it close on its own. Make it look pretty. So it connects. It prints us the flag with a little, because we chose success, it gives us a little plus here, and it exits. This was a really neat way to introduce the various modes of AES encryption, and I had actually learned all this many times over the years, but if you're new to it, hopefully you learned a lot. For me, it was a great refresher. So really enjoyed the challenge. Thanks for sticking around with me till the end. I will talk to you next time.